Hello and welcome to Lecture 8, Applied Security Informed Safety Case Studies, part of the Safety Informed Security Lecture Series for CyBOK. This final lecture brings together the main concepts from the course and apply them for the three SISEN scenarios. The Security Informed Safety course summary shows that we have covered quite a lot of different knowledge areas for CyBOK. Full coverage including introduction to CyBOK, cyber physical system security, network security, physical layer and telecommunication security, risk management and governance, and security operation and incident management. In addition to this, the course also partly covers authentication, authorization and accountability, applied cryptography, human factors, and adversarial behaviors. The course covers several CyBOK knowledge areas because security-informed safety is inherently cross-disciplinary, combining technical security, risk, human factors, operational response, and cyber-physical system behavior. The three applied cases bring these cases together. We began with security and safety foundations and then developed security-informed safety reasoning, wireless and IoT knowledge, attack analysis, mitigation, resilience, evidence, and assurance. The three applied cases, medical IoT, smart building, and six slow-pan scenarios bring all of those elements together. So, for this lecture, we'll first review the common analysis method, applying the security-informed safety and the main categories of attack and disruption. We will then examine the medical IoT case study, smart building case study, and the six slow-pan case study before comparing their common security-informed safety. Let's start with applying security-informed safety. So let's start from moving from concept to applied cases. Applied security-informed safety combines security analysis, hazard, reasoning, and safety consequences. The key question is not simply whether an attack succeeds, but how it changes data, communication, system behavior, and possible safety outcomes. Previous lectures introduced the security failures, the hazards, the assurance, the wireless threats, the safety IoT, and resilience. The applied cases bring these concepts together now within a complete system concept. The same technical event for those three different scenarios may have very different consequences, for example, in different systems. A common case study analysis method that we're going to use for all the different three scenarios will follow the same sequence. We establish the system context, identify security weaknesses, examine the attack or disruption, trace the safety impact, and then consider mitigation, assurance evidence, and residual risk. This provides a consistent basis for comparing different systems. We will also analyze those three cases using three different categories of attacks and disruption. The categories are infrastructure attacks and disruption, communication and protocol attacks, and telemetry and application layer attacks. Infrastructure attacks affect supporting components such as gateway, access point, and brokers. Communication attacks, on the other hand, and protocol attacks affect wireless links and message exchange, while telemetry and application layer attack manipulate values, messages, or system state. An attack may span more than one category. The category identifies where security event occur, not the final safety consequence. Safety analysis must trace how the event affects system behavior. We look now at the first IoT case study, the first scenario, or the first case study. The medical IoT scenario represents heart rate, SpO2, and blood pressure telemetry. Data passes through a simulated BLE to Wi-Fi gateway, and is published over MQTT and displayed on a monitoring dashboard. And the safety concern here is whether the displayed patient state remains authentic, current, complete, and clinically plausible. A patient may be physically deteriorating while the monitoring system continues to present a stable or incomplete clinical picture. The medical IoT system architecture combines several different technologies. You have the wearables that generate the vital signs, the gateway translate and forward them, the MQTT broker delivers them to the dashboard. The dashboard is therefore a representation of the patients based entirely on received telemetry. A technically consistent display may still be clinically misleading. The medical IoT activity implemented in SISEN covers quite a few different things. So we have the gateway and the MQTT observation, spoofed or extreme telemetry, malformed messages and replay. These tests whether false state, incomplete, or implausible patient data is accepted. And the practical demonstration of these activities are covered separately, so here we focus on their safety significance. So let's look at the safety escalation in medical IoT security. False or masked vital signs alter the clinical representation shown on the dashboard. If deterioration is not recognized, the unsafe condition may lead to delayed clinical response. The attack does not directly harm the patient. The risk arising from the attacks does, because untrusted data influences a safety-relevant interpretation. And this is an example of a medical IoT security attack. We move now to smart building case study. In smart building automation, the smart building scenario uses wireless zone sensors, an access point, MQTT telemetry, and a dashboard. It monitors environments and occupancy state. The main safety question is whether the displayed building state remains accurate, timely, and available for monitoring or automation. Automation may respond correctly to the displayed data while still being unsafe if the displayed building state is false or incomplete. So let's have a look at the architecture of the smart building. So similarly to the medical IoT, the smart building system architecture uses sensors, and all those sensors, room sensors, communicate through the wireless access point and publish their state through MQTT. The dashboard then supports operator or automation action. Wireless and MQTT evidence help determine whether a problem begins at the infrastructure, communication, or application layer. A building may appear operational while one room, one wireless mode, or the complete sensor layer is no longer trustworthy. Smart building activities implemented in SISEN includes wireless and MQTT observation, telemetry spoofing, extreme values, replay, noise, single client disconnection, and sensor blackout. You could also use separate access point activities, including hidden SSID observation, MAC spoofing, WEP IV collection, WPA2 handshake capture, and bounded authentication, specifically for confidentiality attacks. The same dashboard symptom may result from application layer injection, wireless disruption, or infrastructure level failure. Smart building security to safety escalation involve false or unavailable telemetry, which can cause the dashboard to present the wrong room state. A hazard may then be missed, or control may be applied incorrectly. Smart building security to safety escalation includes several different things, starting from security event leading to possible harm. False or unavailable telemetry can cause the dashboard to present the wrong room state. A hazard may then be missed, or control may be applied incorrectly. The critical issue is that whether the system recognizes when its view of the building is no longer trustworthy. We finally move to 6LoWPAN case studies. The 6LoWPAN scenario uses constrained nodes IEEE 802.15.4, 6LoWPAN, IPv6, and UDP telemetry with relay into MQTT. You can inspect both the wireless and adapted network views. Safety depends on telemetry remaining current, complete, and correctly interpreted. A constrained sensor network can fail silently from the perspective of a conventional dashboard unless missing or stale telemetry is detected. The architecture of 6-LoWPAN system contains constrained nodes which send telemetry across 802.15.4, 6-LoWPAN which adapts IPv6 to the low-power environment, UDP carries the telemetry, and the MQTT relay make it visible to conventional monitoring tools and the dashboard. Trust in the dashboard depends on every stage in the path. In SISEN, 6-LoWPAN activities implemented include several different activities. Some of those activities, for example, include wireless and protocol capture, MQTT observation, spoofed or extreme telemetry, replay, malformed data, and missing fields. Scenario-focused cases include masked boiler pressure, hidden emergency stop state, and hidden machine overheating. In constrained systems, stale or incomplete data may be as significant as complete communication failure. And the security to safety escalation for 6-LoWPAN involves the security events all the way to possible harm. Replay or incomplete telemetry, for example, may cause an old or partial state to appear current. The unsafe condition arises when a physical or operational change is not recognized. Freshness is therefore both a security property and a safety dependency. We have shown several different activities in this slides. However, there are other activities that were not covered in this lecture, but they are covered in the guide for description and attacks on SISEN repository. Let's now look at comparing the applied cases. So we'll compare the 3 different scenarios. The scenarios use different technologies and evidence sources. Medical IoT, for example, relies on gateway, MQTT, and dashboard evidence. Smart building combines wireless MQTT and dashboard evidence, while 6-LoWPAN adds one layer, which is the 802.15.4, in addition to 6-LoWPAN and UDP views. Despite these differences, each case requires evidence-based reasoning from security event to system behavior and all the way to safety consequences in the same way. For example, we've shown how medical IoT, false, malformed, noisy, or masked vital can lead to incorrect clinical representation. Spoofing, client loss, blackout, or wireless infrastructure weakness in smart building can lead to incorrect or incomplete building state. And we have shown how replay, missing telemetry spoofing, or extreme values for 6-LoWPAN can lead to loss of timely operational awareness, which can lead to hazard and harm. And to summarize, the common mitigation and resilience priorities across all 3 cases is quite similar. Systems must establish device identity and authority, protect integrity and freshness, and validate telemetry. They must detect missing, stale, duplicated, malformed, or conflicting data. When the current state cannot be established confidently, the system should enter a visible degraded or fail-safe condition to protect the data that it's showing to the dashboard. The SISEN repository provides scenario implementation, activity guidance, and technical documentation. There's quite a lot of documentation that I would encourage you to go through. There's also the SISEN student guide, which provide or explains the setup, the operation, the evidence collection, how to stop and recover when you are running the scenarios. And finally, the SISEN hazard analysis and evidence sheet gives you some kind of structured reasoning of how you can record the security events, system effect, unsafe condition, mitigation, assurance evidence, and residual risk for each scenario you are working on. The slide introduces applied reasoning. The repository guidance provides a complete practical workflow and evidence requirement, and the website supporting with all of those recording and all of those practical documents. Remember, security failure must be analyzed in terms of how they change system behavior, violate safety assumptions, and create possible harm. Thank you.